I'm going to suggest that you instantly pause this video and read this small print at the top of the page, and then start again when you're ready to go. Projectile motion is motion where something is thrown or launched. For instance, a catapult, just a thrown baseball, lots of stuff that just is projected. And in the UIL contest, calculator contest, there is always some kind of a projectile motion problem. It is one of the most common things that you do early in the study of physics, because it especially deals with the concept of vectors and vectors in 2 dimensions. And we do them sometimes in the English system of units. And in the English system of units, the acceleration of gravity is always given as approximately -32 feet per second squared. And what that really means is that an object, when it's being pulled by gravity, is pulled downward, and its velocity changes by 32 feet per second every second. So the second squared is not really a squared second, it's a second per second. So a lot of times in studies in physics, when you're studying these things, you first of all learn how to represent that projectile motion with a system of equations, but we'll shortcut that a little bit for you today. And one thing to notice is that if we actually use the most accurate numbers, this would not be something that you would want to do without a calculator. So as we're doing this, I'm going to be punching a calculator for a few problems, and I'd suggest that you'd want to follow along if possible. So the formula that you saw above, Newton's formula, 1/2 AT squared, etc., if I take 1/2 of the acceleration of gravity, that's half of -32 is -16. And notice that what we're saying here is that if we could do a time versus height graph, this is not the path of the ball, this is the comparison of time and height, that we would see that it will go up and then it'll come down. And the height is described by the second degree function. So we're going to use all of our second degree tools to be able to analyze this. So be sure that you understand what our variables represent. And we want to know how many seconds after the ball is thrown will it hit the ground. So we could do that one of several ways. And one of the ways that we could do it is to say that the height when it hits the ground is 0, and we're trying to solve this. And there are several ways that we could do that. One of the ways is we could do maybe a complete the square technique on it. That wouldn't be too bad. I wouldn't even try to factor it because of the size of these, although you might recognize that we could take a 4, just a 2 out of all the coefficients, but even at that, we'd still have some pretty ugly factoring on our hands. So typically what we do with these is we simply go to our calculator, and in the y1, you put in the -16, but don't use t because you have a dedicated button for x, so put in -16x squared plus 30x plus 28, and then in the y2, simply put 0. And you'd be asking, when does this expression equal 0? And notice that we input time to output height, and the question is, when does it hit the ground? When is the height equal 0? And then you simply go to your solver, and you should already have it set up with the y1 and the y2 and your little solution boxes. And one of the things to notice is that all parabolas have 2 solutions. There's a solution in negative time where if it was launched from the ground, it would have reached this height of 28 at time 0 and then continued upward and then come down. So one of the things to notice is that when we give our guess, we should give a guess that we think is right of the vertex point. Now, let me show you a trick, and you follow along. In my calculator, I'm ready to give my guess. I'm going to put negative b over 2a. That would be 30 over 32. And I can tell that 30 over 32 would be a little too small, so I'm just going to add 1 to it. Now, you might recognize that 30 over 32 is a fraction just less than 1, so anything right of 1 would certainly be okay. When you hit the solve, out comes the solution that x, or what we should say is t, is equal to 2 point, and I'm just going to round off at 5.6. And now it asks, what will the velocity of the ball be when it hits the ground? Now remember that when your solver solved it, it also stored that value as your variable x. So I quit to the home screen, and the way to find the velocity when it hits the ground is to remember this formula up here, that the velocity is simply going to be a function of time. So what I want is the velocity evaluated at 2.56. But remember that 2.56 is currently stored in our x value. So the a is negative 32, and the t is my stored value of 2.56. And then the initial velocity is that 30. And hopefully you picked that up when you read the small print above. So plus 30. So all I'm going to do at my home screen is go negative 32x plus 30. And out pops negative 51.88 feet per second for the velocity. But notice that it wants it in miles per hour. So you should have also noticed that we can set up a proportion that we know that 88 feet per second is the same thing as 60 miles per hour. So what would 51.88 feet per second be? So it would be a simple cross multiply and then divide by the 88. So I'm going to take the number on my screen and simply go times 60 divide 88, and out pops the number negative 35.38. And I'm rounding to the hundredth. This would be miles per hour. Now, how do we interpret the negative? And if it says velocity, that's not the same thing as speed. Speed is a positive number always. Think about your car when you're backing up. If you ever dare to look at your speedometer, does it read a negative number? No, it doesn't. So speed is always considered a positive value, but velocity is a directed quantity. So what does the negative tell you? It tells you that it's going down. So this is nothing more than using those skills we've done in the last couple of lessons where we analyze a function in the quickest and most efficient way possible. Now, when we come to this next one, this is not the same as the first one, because this one has reconciled the horizontal and vertical motions into one single equation. So notice that now the input is not time, but rather how far the basketball has traveled in the horizontal, and the output, the y value, is the height of the ball. And then it's given us this equation, so we're going to do exactly what we did a second ago, which is we're going to enter that negative 0.122x squared. And notice again that x is not time this time. It is the horizontal distance, plus the 1.93x plus the 6.5. Now, one of the things that you might notice about this real quickly is that f of 0 is equal to 6.5. That's that thing where the constant always tells you the y-intercept. That simply represents the release point of the basketball during the free throw. So, what is the height of the ball when it's released? 6.5 feet. How far does the ball travel horizontally before it reaches its maximum height? So one of the things to remember is that the axis of symmetry is negative b over 2a. So on my home screen, remember I've already entered this as my y1 equation. On my home screen, I'm simply going to type negative 1.93 divide by open parenthesis 2 times negative 0.122 close parenthesis, and I'm going to store that as x. So negative b divided by 2a. Now notice why we have to have the parenthesis around that. If we didn't, it would only divide by 2, take that answer and multiply by the remaining decimal. It wouldn't double a and divide negative b by 2a. And then I hit the store key. That's the key right above the on key. I stored it as x. And then instantly, I'm simply going to enter on my calculator's home screen y1 open parenthesis x. You don't even have to put the open parenthesis x if you don't want to, because that will automatically evaluate my function with whatever the currently stored x value is. And what I'd see there is that it comes out at 14.13 feet. So what's the maximum height of the ball? 14.13 feet. If the ball's aimed straight, does it go in the goal? Justify your answer. All right, so you need to see that the out of bounds line here is 19 feet from the free throw line. But where is the goal? The goal is at x value 13.75 is the center of the goal, and its height is 10 feet above the ground. So what I want to know is at this x value, what's the height? So all I have to do on my home screen again is to call up the y1 function, and on the y1 function, oh, I'm sorry, I skipped one. B, how far does the ball travel horizontally before it reaches the maximum height? All I have to do to find that is to simply evaluate this part of the thing. Now, I didn't write it down, but I did store it as x. So if I just type x on my keyboard and press enter, it will tell me that this distance here was 7.91 feet. So as a coordinate, I could put that as a 7.91 and a 14.93. So about 7 feet in front of you, it peaks out. Now it's coming down. Now we wonder, is it going to go in the hoop? So what I'm wondering is, how high is the ball when it's 10 feet away? So I simply evaluate my y1 function at an input of 10. So that looks on your screen like y1 evaluated at 10, and it comes out at 13.6. So it looks to me like that's a difference of 15 hundredths of a foot. And 15 hundredths of a foot is 15 hundredths of 12 inches, which is equal to 1.8 inches. So you're within 2 inches of the center. Surely you made it. You might know this if you're a basketball player, that the ball is roughly 9 inches in diameter, and the hoop is 18 inches in diameter. So surely if you're within 2 inches of the center, it's going to go in, assuming it's straight. So these are all those same skills that we've looked at. Now we're just doing it in application. So suppose there were no goal or wall to stop the ball. How far would it travel horizontally before hitting the floor? So it looks like it would hit somewhere near the end line, but the way that we find out is we ask, not that. We ask, what is the x value that makes this work out to 0? What is the x value over here that makes the y value 0? So we're asking what input does that. So back to your y1, you should already have the y2 as a 0 from the previous problem. So all we need to do is to go to our solver, and one of the things to notice is we'll find this right-hand point if we'll put anything to the right of 7.91, or you can even just make a guess. It looks like it's around 19 feet, so let that be your guess. And it turns out that it's 18 point, I'll call it 6-7 feet. So it looks like it would hit just inside the end line if it didn't hit the backboard or the rim or anything else. So we're just using the technology to help us out as much as we can. Sometimes it's easier not to use the technology, but this particular lesson is like a physics class where everything is going to be done through the calculator. One of the things to note, you can solve, in that previous problem, you could have solved for this point where it hits the ground using the quadratic formula. Why would you do that when you already have the equation in your calculator, and your calculator has a function built in that will solve that instantly? So here's the kind of problems that you're going to look at. For the most part, you've already been given the equation. All you need to do is to recognize, what does the t represent? What does the d sub t? And we had a lesson early on that was trying to get you to focus. How does any function work? Input, output. How does this function work? So we'll just work those problems and deal with the problems as they arise. Good luck.